Hi everyone, my talk today is Pwning blockchain for fun and profit, and I'm going to share a bug in Solana me and my friends found a while back. Here's a quick introduction of myself. I'm Ginoah, a former red teamer and CTF player with Belson. I'm also a co-founder of Anatomist Security, where we focus on blockchain auditing and consulting. Unless you've been living in a cave for the last few years, there's no doubt you heard of blockchain at some point. Likely along with all kind of description, stuff like Bitcoin to the moon, NFTs, future of finance, and all kind of other snake oil. But none of this really explain what a blockchain is. Let's be simple. Blockchain is essentially a distributed database built to operate with minimal trust among its nodes. It uses a consensus algorithm to detect and penalize misbehaving validators. Modern blockchain also offers smart contracts. Script run on custom virtual machine that automate transaction and enable decentralized applications. The target we're looking at today, Solana, is one of those modern blockchains. It is written in Rust, uses a variant of BFT algorithm with proof of stake for consensus, and include a VM that runs a custom modified fork of eBPF, which is called RBPF. We can understand RBPF simply as a VM runtime for smart contracts, or what we call program, which is written in Rust also. And before we get started, the bug presented today is introduced in an optimization-related feature in release 1.16. We reported approximately a year ago, and the bug has since been patched. Here's the index of today. We'll begin by discussing some basic concept of Solana, then we'll dive into the legacy model, how validator load account data from database, execute a program, and then commit the result back to database. After that, we'll explore what direct mapping is and why it is important. We'll also look at how the new model changes after direct mapping is introduced. Finally, we'll talk about the bug and exploits. Now, let's begin with some basic concepts. As mentioned earlier, blockchain are basically just databases. So it is easy to see that keeping track of some persistent data or state into its storage is the main purpose. In Solana, the data are stored in key value pairs, where the key is some 32-byte identifier, which we usually call address, and the value is a data structure called account. Account includes several fields, such as lamport, which is just a fancy name for the Solana token balance of an account. Other fields like data, which hold general purpose data created by Solana program, is also tracked by accounts. And the other crucial part is transactions. Everything we want to do on a blockchain happens through transactions. Now, there are two key components of a transaction, instruction and account. Instruction are basically individual call to a program. This could be system program or a smart contract written by the user. A single transaction can include a multiple instruction. And it's atomic, which means if any instruction fails, the entire transaction is rolled back. Then we have accounts. In a transaction, we have to specify all the accounts that might be accessed during the execution of all the instructions. These accounts are split into two sets, a read set and a write set. This marks them as read-only or writable, allowing Solana to execute non-conflicting transactions in parallel. So let's dive into the background of how Solana managed data storage during transaction processing. Let's start with looking at the original 1.14 internals, which we will refer to as legacy mechanism from now on. This is how VM accesses its data. The RBPF runtime memory layout is straightforward, with 4 sections. Similar to other common process layout, there are code, stack, heap, and an input section where data loaded from database is stored. Each section is assigned a fixed size and virtual address. Here's a view of how accounts are loaded into virtual memory. At the beginning of every transaction, the account list mentioned earlier is loaded from the database and stored in the account shared data structure within the transaction context. Later, these accounts are serialized into the input region, allowing the VM to access them. For example, account 0 and account 1 are serialized into the input section, with all fields such as the key, owner, lamports, and data being serialized together. After loading the account into memory, account info structure are reconstructed from the serialized data. This is done to make life easier for contract developer to interact with account passed into the VM. An entry point routine within the RBPF program constructs account info structure used by Solana programs, and this account info structure are stored on a heap. Key attributes like owner, LAN port, and data in account info reference back to the corresponding memory in the input section, so any change made in the account info are directly reflected. During runtime, the RBPF program has full control over its virtual memory space, so user can manipulate memory within the VM however they want. Recall that accounts are loaded into the input section, regardless of whether the account is owned by the program or not. So we need to implement some sort of permission check to prevent someone from modifying the LAN port of another account. Since all the data inside the VM is temporary, the main thing we care about is the account's write permission when committing the execution result back to the database. There are a few rules that must be followed. For example, the account must be marked as writable in the instruction if the program wants to modify its contents. Only the account owner can modify its account data or decrease its LAN port, and the total sum of LAN ports has to remain consistent. For simplicity, let's say that only the account owner has the permission to write to the account. At the end of the execution, the data in the input region is deserialized and written back into the per transaction account cache, which is transaction context. This is where all the checks are applied. All the validation rule we mentioned earlier must be satisfied before writing back into transaction context. After execution, if the entire transaction succeeds, the context within the transaction context are committed back into the database. The data is persisted, the transaction ends, and then it moves on to the consensus process. And that's it. Deploying a contract and calling it from an external owned account is simple. But what if we want to implement a more complex system that requires interaction between multiple contracts? We will need a more sophisticated mechanism to pass data between VMs. This is where the CPI, cross-program invocation system call, comes into play. First, let's take an overview of legacy CPI process. When one program tries to invoke another, it crafts an instruction and calls the CPI syscall. The instruction is analog to instruction in a transaction and specify which program to call as well as all the account involved. It first fetches the account metadata specified by the instruction to learn which account are used, as well as whether they're writable and whether they're a signer. Next, using the public key, it took up the corresponding account share data in the transaction context. This allows us to write the validated change back into the transaction context later, which serves as per transaction cache. The third step is to retrieve the account info corresponding to the public key and translate the virtual address, such as LAN port and data, into host pointers. These pointers are stored in a structure called caller data, so they can be used later easily. Finally, we have the account info we needed and account share data as a cache. We then go through the validation rule mentioned earlier. Once validation is complete, the data is written back to account share data. And later, when actually executing the invoked program, the next program will serialize this account into its input section, just like we talked about before. At the CPI boundary, all changes to account must be validated to ensure they are legal before passing them to the next program. Otherwise, we risk allowing illegal updates. Since Solana program does not allow graceful handling of failure in CPI caller program, the VM can safely assume that if the callee fails, the entire transaction will be reverted. This allows the VM to treat CPI boundary as checkpoint and flush all validated change into the per transaction cache. The design allows the VM to reuse the account cache while serializing data into the CPI VM memory. Leaving the CPI scope is similar to finishing execution. except change to account data must be written back into the parent program's VM memory to reflect the updates. Just like when exiting an outermost instruction, we retrieve the account from VM memory, go through the validation rule again, and then write them back to account share data. Before writing the data back to the parent program, we check if the original VM has preserved enough space for potential data growth. The amount of preserved memory is controlled by the constant, which limits the account data growth per transaction. If the child VM attempts to grow data beyond this limit, the transaction reverts. Once the check is done, we can simply copy the data and other property back from account share data into the parent program's memory. So, it works, but the current serialization-deserialization-based account pathing schema require one copy when entering a new context and another when leaving it. These data copies are costly and create a bottleneck for execution speed. To address this, an optimization called direct mapping was introduced in version 1.16. The overhead only becomes significant when the length of data being copied is large, so we only need to avoid copying data field. Also, copying is not necessary when reading account data. It's only required to prevent data pollution when writing to an account. With the new direct mapping mechanism, this is what the new data exposure looks like. Instead of copying the entire buffer, it directly maps the data vector buffer into VM memory. We can think of the legacy input section as a single block that's allocated all at once. The new data exposure breaks the input section into multiple parts, with some portion residing inside memory specifically allocated for the VM, while account data directly mapped to the actual data vector owned by account share data. Due to the direct mapping of account data, VM writes to those memory are now editing account cache data directly. Thus, every single write to the map region must be validated. Failure to do so could allow illegal writes to succeed. The view of account info structure for Solana program remain unchanged. The key, LAN port, and owner still point to the serialized data in the input section. However, the data field now points to a directly mapped section. When data is written, the VM now resolves the corresponding virtual address to a host shared memory, instead of memory dedicated for the VM. Now that we have a basic understanding of the new data exposure, let's cover two concepts we skipped earlier: how copy on write is achieved and how VM manages its memory. Remember the data in account share data, which is reference of a vector. It actually points to the same data buffer as another account share data instance in the account database cache. The data is only copied when a write occurs. When a data write occurs, a new copy is created. However, the legacy implementation doesn't guarantee that the data will only be copied once. Recall the reserved data buffer within the serialized content in the input section. This buffer is reserved to handle potential growth in an account data length. Whenever we increase the data size upon entering or leaving a CPI, whenever the account share data buffer is not large enough to hold data that should be written to it, we need to reallocate the account data buffer, resulting in an additional copy. Every time we relocate a new data buffer, we have to copy the old data into the new buffer. Note that only the data reference in the transaction context is updated, while the data reference in account DB cache is only updated when committing the transaction. The new data exposure mechanism aims to eliminate this excessive relocation by reserving a maximum bytes of spare memory during the very first copy on write. This ensures that in the majority of cases, at most one relocation is needed for the entire transaction. The second concept we're exploring is how VM memory is managed. Early, we thought of VM memory as an isolated space and only occasionally mentioned translating VM address into host pointer. Now, let's see how these addresses are translated. There is a structure called memory region that records the mapping between host pointer and guest address. along with field like data length and an isWritable flag. Every time the VM tries to access a virtual address, it locates the correct memory region, translated the guest address to a host pointer, and then finally access it. In the legacy model, memory regions have their own dedicated buffer, with each section, such as input, have its own memory region mapped to a single large buffer. This memory region remains unchanged throughout their entire lifetime. However, in the new model, the data buffer is directly mapped into VM memory, but the other fields are not. To be more specific, when the VM tries to read or write account data, the address is mapped differently. Instead of pointing to the input section's buffer, as in the legacy model, it now points directly to a data buffer on the host heap. This buffer is shared with other structures. The other field remain unchanged. When accessing field like LAN port is still resolved to a dedicated buffer, just like in the legacy model. This requires us to split the input section into multiple memory regions. It's worth noting that the memory region structure has also been slightly modified. We will talk about this later. Another thing worth noting is that the host address in the new memory region may change due to data relocation. Recall that we need to relocate to a new buffer when the data grows. This is the old buffer. When the new buffer is allocated, both the pointer in account share data and the host address in memory region must be updated. But all other fields except for state remain consistent throughout its lifetime. This means the reserved data buffer doesn't benefit from direct mapping. When trying to write into the growth area, the guest address actually points to the reserved data buffer, not account 0 data, which isn't mapped. Therefore, it still requires an additional copy to the actual data buffer during account writes. Now, let's talk about the state field in the memory region. There's a state field in the new memory region structure that we haven't discussed yet. This field is crucial for permission check on data writes. So let's see how it works. The readable and writable state correspond to the isWritable flag in the legacy memory region. Previously, the entire input section was marked as writable, as it contained both accounts that the program had write permission for and account it didn't. This meant we had to perform data write check retrospectively when exiting the VM. Now, with direct mapping for account data, we need to apply check immediately as the write occurs. This is done by assigning the correct readable and writable flag to the memory region overseeing the data buffers. The copy on write flag is used to handle the buffer reservation we mentioned earlier and serve no other purpose. Once a copy occurs, it changes to writable, so we can ignore it from this point onward. To summarize, we only need to focus on the permission of memory regions that are directly mapped, as all other fields will be validated when writing back to account share data. Managing memory region access using state means we need to know the permission upfront. Fortunately, the rules are consistent with a single VM context. For example, only the account owner can modify data, and account fields are writable only if the account is marked as writable in the instruction. Now that we know which permission to assign to memory region during creation, let's see what happens when we try to commit the accounts. The process is quite similar to before, except for updating the data buffer. For other fields, such as LAN port, we simply validate them and write them back into account share data. For the direct mapping data buffer, the section from the startup to the original length has already been modified through direct mapping. However, if a write has occurred and the data length has increased, we still need to update the data beyond the original length and update the data length. As that part is still in reserved buffer, we have to perform an additional copy. With data writes handled, the next thing to understand is how CPI works in the new design. The CPI code is quite similar to the original design, but we don't need to copy the entire account data anymore since it's now directly mapped. Most of the process remains unchanged. First, we retrieve the metadata of the account involved in the CPI instruction. and then we look up the corresponding account share data from the transaction context. Then we translate the guest address in account info into host pointer to construct caller account. And here's where things differ. Instead of copying the entire account data, we only have to copy the newly grown data that is still in the reserved buffer back to the newly allocated direct map buffer. Finally, we validate other account changes and write them back to account share data for further serialization. The major difference occurs when returning from a CPI call. Since we're using direct mapping, and a vector copy and write might occur during nested calls, we need to check if the original data buffer mapping has been relocated. If the data buffer has been relocated, we need to update the original mapping in the parent program's memory region to reflect this change. Just like when entering a call, when returning from CPI, we need to copy the data from the reserved buffer back to the direct mapping data buffer, validate all other changes, and then write them back to account share data. Second, we check if the data buffer has been relocated. If it has, we need to replace the parent's data mapping to reflect the change. The rest following the same process as in the legacy model. We perform some check and update the account change back to the parent program. So, how exactly do we perform relocation check and update data mapping in memory region? Remember, mapping are managed through memory regions, each containing a non-overlapping range or virtual address. We also have a VM data address that stores the virtual address of data in the parent VM. The solution is straightforward. We look up the memory region corresponding to the given VM data address, where VM data address should match the VM address in the memory region. Then we have the memory region mapping the data buffer, which is still pointing to the old data buffer. Next, we check if the host address matches the current address of the account data buffer. If they don't match, it means the relocation has occurred. So we update host address in the memory region to current address of the account data buffer. After updating host address, the memory region now correctly points to the newly allocated buffer. Finally, now we have covered all the background mechanism we need to understand. So, finally, here's the bug. When returning from CPIs, in the replacement procedure, update caller account is called. We search for a memory region with VM data address in caller accounts, and then update the host address if host address in memory region doesn't match the address from account share data. Here, two questions arise. How does the CPI know which region to update, and where does that virtual address came from? We search through the list of memory region for matching virtual address, but the virtual address we compared against it came from caller account, which is constructed using information of account info from the VM heap, which means it is fully controlled by the user. Nothing ensures that virtual address point to the correct data for the account. So here's the plan. Let's prepare two writable accounts of different length, account 0 and 1, mapping to memory region 1 and 3. By modifying the VM address in caller account, we can make it fetch the wrong memory region when updating account 1, causing memory region 1 pointing to memory region 3's data buffer. And the data length of account 0 is longer than account 1. After the replacement procedure, the host address in memory region 1 will point to account 1's data buffer. This allows us to use account 0's data pointer to access account 1's data. Since both accounts are owned by our program, there's no permission issue. But notice that account 0's data length is longer, so when accessing the data part of account 0's data, it will go beyond account 1's data buffer. This gives us out-of-bound access to the host memory. Here are the detailed steps to gain arbitrary memory read-write primitive. First, we need to prepare 3 accounts owned by the attacker program. Here's the initial state. We omit memory region irrelevant for this exploit and only show memory region 1 and 3 and 5, which corresponding to account's data buffer that we'll be using. Similarly, we only show account share data for account 1, since it's the only account that will be passed through CPI to trigger our exploit. Notice that the data buffer for account 0 is larger than those for others, We will leverage this size difference for out-of-bound memory access. The first step is to modify account 1's account info data pointer in the ref cell to point to data buffer of account 0. Then initiate a CPI code that includes only account 1. This will construct a caller account for account 1, but its VM data address will point to data buffer of account 0. In the calling program, we return without doing anything. When CPI returns, it initiates the replacement procedure, checking if the data buffer of caller account has been relocated. It tries to retrieve the memory region using the VM data address in the caller account for account 1. But instead of finding memory region of account 1, it finds the memory region of account 0, believing it is the memory region of account 1. Next, it compares the host address in memory region 1 with the data pointer in account share data 1. Since account share data 1's data pointer correctly points to account 1's data buffer, which is different from the host address, it assumes the data buffer has been relocated. It then updates the host address in the memory region 1 with the data buffer of account 1. This causes memory region 1 to point to the incorrect data buffer. And since account 0 data buffer is longer than account 1's, this gives us an out-of-bound memory access. Next, we attempt to scan and egg hunt memory region 5 on the host heap. We can simply revert the transaction and try again until we successfully find memory region 5. Once found, we override its host address to point to wherever we want, giving us read-write access to arbitrary address. For example, let's say return address on the stack is located at 0x.bif. We simply override the host address of memory region 5 to 0x.bif, then write to it through account 2's data buffer. This allows us to hijack the program counter when returning from program execution. From there, we can build a ROP chain to gain remote code execution. Here's the demo. On the right, we have two windows for the attacker with IP 0.2. On the left, we have the validator running with IP 0.3. First, we start the validator with version 1.16 and all default configurations. We also have uncat listening on port 10101, waiting for a reverse shell. The exploit script deploy our attack contract, airdrop the necessary funds to the involved accounts so they can pay for data storage, and finally trigger the exploit. Let's wait a sec for validator to handle the transactions. As we can see, the reverse shell connect back from the validator, and we can, for example, cat the validator node's private key. And that's pretty much all I have to show for today. But before ending the talk, let me share some of my thoughts on the state of blockchain security. First and foremost, blockchain security isn't just about dumb smart contract bugs. As we've seen today, the infrastructure behind blockchain is incredibly complex, with the software constantly evolving and under development. Where there is complexity, there will be bugs, and sometimes even interesting bugs that are just as sophisticated as those we see in other well-established targets. I know a lot of security people who dislike blockchain due to the culture around it, but honestly, just give it a try and you'll see it could be quite an intriguing and lucrative target. Secondly, it's also worth mentioning that this is the prime example why low-level exploitation wouldn't die even if people switch to so-called secure language. There is always need for optimizations or low-level programming which use unsafe code. As long as people resort to unsafe code, there will be bugs. Finally, what I've touched today is arguably the simplest part of blockchain. While blockchain are kind of a product without a demand, it's actually pushing the frontier of several fields, ranging from consensus algorithm to zero-knowledge proofs. There's an entire range of topics to be explored, and new technology often comes with new security issues. Hence, I love to invite people to hop on the party and join us in breaking blockchains. Thanks for listening.